Today we're going to start talking about radioactive isotopes. Now, when you think of an isotope, just remember, an isotope is an element with the same number of protons but a different number of neutrons. Now, some isotopes are going to be stable, while other isotopes are going to be unstable. Again, most of the isotopes listed on the periodic table are going to be stable, but it is going to be their other forms that are going to make them unstable. The proton to neutron ratio is going to be key in determining what is a stable isotope versus one that is unstable. The closer that isotope is to a 1-to-1 ratio, or the closer that proton to neutron ratio is to 1-to-1, the more stable that isotope becomes. Radioactivity, that is the process of an unstable isotope breaking down, meaning that again, it does not want to be unstable. Everything needs to find a way to become stable. And if it's not stable, if it is unstable, it'll go through this process of radioactivity to break itself down to become more stable. During that process of radioactivity, an isotope is going to release radiation. Radiation is just going to be particle or energy emission from an unstable isotope. So during that process of radioactivity, it's going to give off radiation. Now, there's three types of radiation. The first one is going to be alpha. Alpha is just going to be a helium nucleus that is given off during radioactivity. And what I'm saying is it's basically 2 protons and 2 neutrons. Now, if we look at alpha in isotopic notation, what it's going to be is 4,2He. Again, that's going to be important for when we go ahead and begin writing nuclear reactions. So again, it's a helium nucleus given off during radioactivity. Again, just reminding you, isotopic notation, this is your mass number on top. Your atomic number is going to be listed on the bottom. Your second form of radiation is going to be beta, and this is going to be a high-speed electron given off during radioactivity. Now, the thing I want to tell you is, because again, protons and neutrons weigh something, electrons, they do weigh something, again, not very much, but these are the 2 forms of radiation that are classified as matter. So alpha and beta. The thing about alpha is basically stopped by the skin. That's how weak it is. Beta can penetrate through the skin, but basically is going to be stopped by the bone. If we look at beta in isotopic notation, it's just going to be a 0, -1, and then B. Okay. Again, remember, there is no mass number associated with an electron, and then again, this atomic number down here on the bottom for this type of radiation is just going to be a -1. The last form of radiation, which is going to be your strongest form of radiation, is going to be gamma. Gamma is just going to be high energy waves. And again, remember what I said, alpha and beta, those are going to be forms of matter, and energy is not classified as a form of matter. But again, it's high energy waves that are given off during radioactivity. Basically, this one can pass all the way through the body, pass through the skin, pass through the bones, and basically it takes a lead plate to stop gamma radiation. If we look at gamma, gamma is going to be represented like this, Y and then 0, 0. The thing about gamma radiation, you'd never really see it by itself, because again, if it only existed as itself, its mass number would never change, its atomic number would never change, and therefore we're not going to be changing the nucleus of it. So usually gamma is going to be accompanied by one of the other forms of radiation, either being alpha or beta. When we talk about chemical reactions and you think of Antoine Lavoisier and the law of conservation of matter, what he's saying is those atoms, they're going to be rearranged, but the atoms or elements that we start with are going to be the same elements and atoms that we end with. It's just going to be bonds are going to be broken, new bonds are going to be created. But again, you have the same elements before and after. In a nuclear reaction, that isn't always true. What you start with is going to completely change into something different or something brand new. A nuclear reaction is just going to be any reaction that involves a change in the atom's nucleus or produces a different element. So again, we're changing the nucleus, and when you change the nucleus, remember, your atomic number is what's going to be your identity of your element. So let's go ahead and look at an example. It says thorium-237 goes through 2 alpha decays, 1 gamma decay, and a beta decay. Write the complete nuclear reaction. What we're going to do is, anytime you're going to be writing nuclear reactions, the first thing you need to do is write it in isotopic notation. So I said that we're going to have thorium 237. When you look up on the periodic table, the atomic number for thorium is going to be 90. Here's the thing. It tells you that it goes through an alpha decay. It actually tells you it goes through 2 alpha decays. But if we're going to write the complete nuclear reaction, we have to write it step by step. I told you that. 1 alpha decay was going to be 4,2 He. Now this is really like a math problem where this is your answer over here, and these are going to be the 2 parts. So it's kind of like plus x. So I've got, again, the 4,2 He. So what I have to do is I have to figure out what x is. So 4 plus what gives me 237? Well, again, when I go ahead and do that and do the subtraction, I know that 233 plus 4 is going to give me 237. Same thing on the bottom. My answer is 90. And I've got the 2 over here from the helium. 2 plus 88, that is going to give me my 90. So I need to look up on the periodic table. The element with an atomic number of 88 is going to be radium. Okay? So again, you look at your periodic table, find atomic number 88, and that's going to be radium. All right, so now we're working with this. Okay, so again, it says we have another alpha decay. So that's again going to be a 4,2 He. Again, I told you it's just like a math problem. So 4 plus what gives me 233? Well, that's going to be 229. 2 plus what gives me 88? Well, that's going to be number 86. And again, when you look at the periodic table, number 86 is going to be Rn, or radon. Now, it tells you it goes through a gamma decay. Well, again, remember what gamma is. 0, 0. So this is the reason why I told you that gamma has to have something else. We have a 0 for a mass number, so again, that's just going to leave me with the same 229. 0 plus 86 is still going to leave me with that 86, and it's still going to end up being radon. So what I'm going to do is I'm going to go ahead and come down here because I don't have enough space to go straight through. So 229, 86, and again, that's radon. Now the last thing it tells you is it goes through a beta decay. And again, beta is just going to look like that. So 0 plus what gives me 229? That's going to be 229. Now here's the key thing. Look at beta. It shows you here that that's a -1. So again, it's kind of like, this is going to be an x here. So -1 plus what gives me 86? Well, what that would be is 87. So 87 minus 1 will give you 86. And when you go ahead and look up on the periodic table, that ends up being francium. So when you go through this and it says write the complete nuclear reaction, I need to see all of these steps.